We continue on.
Yep.
Daniel's going to introduce the next concepts.
Right. So I think we've got the hang of generating surfaces and how do we run badlands.
Maybe you can introduce yourself.
Oh, hey, I'm Daniel. I work on this project, Baselands, usually in the CTDS center, where I sit here sometimes as well. Initially, I worked with Jody on Base Reef. Everyone remembers that. And yeah, so now I'm working on badlands and baselands. So we're gonna start off with creating, let's say, a surface for baselands to use. We already have examples in the PyBadlands called the creator, which we'll use. But if you want to generate it, we have a script here. It's simply just gonna create a surface based on these parameters and how much simulation time you're gonna give them. And if you just run this, it's gonna run for a few seconds. And it'll tell you that the output has been saved in the data folder inside Creator. You can generate different topographies for each example just by changing the directory from Creator to other examples if you have them on your laptop. It could be like the eTopo, continental margin one, or mountain, or any other thing. And so once you have this generated, we can start using baselands. This input file has been saved inside the creator folder. You can check it inside data. There'll be a resolution for creator.csv that basically contains the initial topography that Baselands is gonna work on. And this has also generated our simulated final topography and final erosion deposition maps because we've run it once. This is this baseline is going to use to generate the RMSE values and the likelihood values. So we're back. So then we can start on this script. It's called the Baselands creator example, where we run a simple MCMC, Bayesian inference on a Badlands model. So if you go into the script, I've given the explanation just as Rohit showed you in the slides. We have our data as D, the parameters are denoted by theta, and we're trying to find the posterior, which is the probability of theta being unconditional on D. So essentially what MCMC does is it sort of samples from some known distribution. It evaluates the criteria based on the likelihood. If it likes it, it accepts that solution and starts the process again from the new point. And if it doesn't accept the solution, then it stays at that current point in time. I think that's denoted by the algorithm and the visualization we saw earlier. Again, we're just going to pick an initial value of a parameter. We're going to add some random noise to it using a simple Python line where it picks a value from a uniform distribution. We're going to approximate the likelihood, like this part is going to be done by our script. Currently, the script won't have this code, but I'll show you where in the back there's an MCMC script which calls the function. For the Jupyter notebook, I've just put this as a wrapper for you guys to just use as a black box. But I'll show you where all this stuff is happening inside the Python script as well. So let's start by... Actually, let me just finish this up. So this is good. Badlands is gonna return a likelihood value at each sample, where we're gonna either accept that sample, so then it moves on from the new one and repeats the process again till we reach a maximum number of samples. If it doesn't accept a sample, it stays at that position and then draws again, and then again computes the likelihood. And if this ratio is basically greater than this uniformly picked value, it accepts it, and the process goes on. Any questions on this? So this is essentially the same thing that Rohit just explained. So we're just going to go through the code. This is what's going to come out of it. So in essence, for one of our experiments, the simulated data had 1.5 as the true value for rainfall, and 5 to the power -6 as the erodibility. So when we ran an MCMC scheme, like a single chain only, For 100,000 samples, this is what the posterior distribution gave us. Again, the lines essentially mean that this red line on the rain posterior corresponds to the red line on the erodibility one, indicating that this is the combination that gave you the best result. And the second graph, as Nathan pointed out, this is essentially how the rain parameter and the erodibility parameter changed over time during the MCMC sampling process. So on the x-axis is the number of samples. So on the 20,000 samples, the rain value was 1.8, while the erodibility was somewhere between 0.425 and 450. And again, it explores the surface. We can have a look at the surface. Wait, I have it somewhere. So again, for creator, like even though we can't visualize this for more than 2 parameters, but it does help understand how the MCMC scheme is going to work. The MCMC scheme sort of started somewhere over here, and it's only going to accept likelihoods that are better than it was before, with a certain probability, and then it leads up somewhere. So any of these would give you a very nice looking topography, which would be very similar to what the ground truth that you just simulated. And that is what's denoted by the distributions here as well. So the red point here and here would be 1 point on that surface. So we're going to start running this MCMC script. You just do a shift enter on the first cell. This is just to import the MCMC script that we have at the back and some other dependencies. So this is where we're going to initialize all the parameters that we need for MCMC. We can also get outputs in like .h5 format for all these things, but they usually tend to take a lot of the memory space. And since we're going to be running 100,000 simulations, ideally we won't like to save them. So we provided an option of muting the output for each sample and each run. So if it's true, then it won't really produce all the .h5 and output files that it usually does produce. And run number is just so that you can keep track of which folder contains which run. So we have an option of also having the likelihood of sediment as true or false. So the likelihood surface, essentially, this one is a combination of both. So we've compared the elevation difference between both topographies and also the sediment difference. But you can choose to keep either one of them or both of them together based on topographies and stuff. So for mountain, we don't have a sediment component, so then we have an only option of using the elevation as the only tool to measure the difference between the two topographies. Right, so that's likelihood sediment is false, we can keep it as true. So the thing that Rohit mentioned about comparing the sediments, now in ideal scenarios, we won't have the sediment calculations of the depth of the sediment at each point on the grid. So to keep it realistic, we picked a few points arbitrarily on the grid where we're going to compare the sediment at like 4 intervals during the simulation. And that is going to be included into the likelihood calculation. So you can,
it might be like drill cores or something.
yeah, this might be certain points that you're interested in the grid where you can feed them in, and this will essentially be the anchor to which sediment is calculated.
So why is it done at certain intervals during the month runtime?
Like we can do it so we can either do it from the start till the end, and like we have a ground truth and the sediment was this at the start and at the end. And then we run the model and we can only compare at the end, but we thought we benefit from having it at certain times as well, because there could be multiple different ways where the sediment could be the same at the end. Maybe it follows a different path.
I think that actually when we were doing this work, each month I emphasized that we should do this part to people when interest in the geoscience.
We can have more intervals as well. Like currently we've chosen 4 for simplicity. And then we can choose which example we want to run baselands on, like the creator, mountain, or any one of the folders that we have there. The XML input just reads all the parameter values that are in the XML file, for example, rain, erodibility and stuff. And then we can give the number of samples we want the MCMC chain to run. Usually this is a high number, we can use 100,000, 50,000. But for simplicity, just for a test run, we can do 100 maybe. And the simulation time for how long you want the topography to be run by Badlands. We also, so these are the priors that we were talking about. So the rain limits essentially provide you a flat prior with the min and max value. So you can have a minimum rain of 0 and maximum of 3. You can change this. Currently, we've only implemented it as a uniform, but if you know more information, we can have a normal distribution around it as well. Same for erodibility, M and N. Currently, this example for MCMC, we've covered only 2 parameters, rain and erodibility. We also mentioned the true rain and true erodibility for purposes of displaying the posterior distributions. Can just form a line wherever the true value is. Oh, we have 2 likelihood sediments. That's true. So these are all the initialization parameters we need for the MCMC. We can tweak them as we like, and later Nathan's going to mention how we've increased them in parallel tempering as well. So, yep.
Can you explain again what is the RGP course?
Oh yeah, so those, well, that stands for erosion deposition coordinates on the grid. So essentially, we compare the sediment deposition at different times for the simulated topography with the actual ground truth. So Dietmar, you said that usually we won't have the information throughout the grid. So that might overemphasize the sediment in the likelihood calculation. The number is just a coordinate on the grid. So for example, if the grid is... Oh, no, those are nodes. So for example, if the grid is 200 by 200, this is like the 60th point on both axes. So the scale can change, like one node can be 5 kilometers or 1 kilometer.
They're essentially randomly selected.
Yeah, essentially you can change these coordinates. You can have any number of them. Or...
Do you have like a formula to know which samples ideally you should aim?
Again, it's a bit of trial and error on that. Like we can run a few, like let's say we can start off for crater, since we already know the likelihood surface, we know that we don't need that many samples for it to converge. You can also create a likelihood surface if you would like. We have a script for that as well, but again, that is a bit time consuming and stuff. So on a ballpark, I think starting for 2 parameters only, we can get away with like 4,000 samples or 5,000 samples, something around that, from experience.
So the goal is that these are the methodologies that we have developed, and it's like kind of for people from their respective areas, if they want to do an application of baselands, right? So in that application, they will know if they have sediment information. If they don't have sediment information, then basically you can call it as false, and then sediment won't be accommodated in the likelihood. If you have sediment information, then obviously you will know where those sediments are in which coordinates, and then you can put it in there. But it's all dependent on you. But what we did, why we picked them, we just wanted to demonstrate that this is the way to do it. You will just replace those coordinates, and even the intervals, the sediment intervals. And maybe because these sediments usually they get from a drill cores, and after analyzing drill cores in some study, they may have found that okay, in this area there was this level of erosion deposition in this X and Y coordinate at 5 million years and 13 million years. Only at 2 times they know. So it may not be regular intervals, right? So, but that could be accommodated into the Badlands specifically.
I think that's the initialization of variables. This is just to create the output directory so you know what stuff goes. So first 3 lines are just reading the files that the earlier script created, which is the ground truth that it's going to compare against. So we've called them final, like the final elevation model that we have and the final erosion deposition. So we have the final erosion deposition because we initially compared the entire grid. We can do that still. Like instead of just providing coordinates, if you would like, like the topography to compare every point on the grid for erosion deposition, you can do that as well. And then finally, we just set some directories for the results to go in. And this is essentially what makes a class of the MCMC sampler. We've provided the parameters that we just initialized, like whether it's muted, what simulation time there is, how many samples. These are the final things that the ground truths, and it's going to compare against the erosion coordinates, the file name and stuff. So you can also do a help, and I think the description is there. And then finally, you just need to run the sampler. And this should start running. It'll give you the initial values that it started on. So it's going to start at a different initial value every time. If you're lucky, like the rain can already start near 1.5 and it won't need to change range that much. And so on for each one of them. Now this is going to keep running. So since we've run it for 100 samples, it's going to go till 100 here. Should just run 20. It's going to provide you with what the, well, it's just for information purposes, what the likelihood was at this particular point and how the likelihood differs from the current to the proposed. And then it's also going to tell you whether that sample was accepted or rejected. So sample 10 was accepted, 11 was accepted, 12 was rejected, which means it's going to start again from wherever it was in the 11th sample. And so yeah, after you're done with this, let's just wait a couple of minutes. Oh, I can start showing you the script, and if you want to tweak it a bit. So if you go back to the BayeslandsWorkshop, in the examples folder, there's a thing called scripts. You have the MCMC script here as well, which is essentially the entire code. It's not very readable. That's why we created the Jupyter notebook. So you can tweak stuff here. This is the main Badlands model, which just takes in the parameters and gives you an output of the topography, which is later used by the sampler function, which is down here. This is the likelihood function, which with the equations, and it essentially takes in the real simulated truth data and the data that's provided by the Badlands model, and essentially just calculates the RMSE or sort of the likelihood function here. And if we've like put the likelihood sediment as 2, it's going to add the sediment component. Otherwise, it's just going to include the elevation one. So this is where the sampling begins. It's just initializing variables. So the first major part is picking the initial point from where the sampler starts. This is where rain and erodibility is chosen. For simplicity, we've kept M and N as constants in this example. Here we add the random noise. So here's the sampling started for the number of samples that you've put. It's going to add noise. It's going to check whether the rain and erodibility is still in its limits. And here it's going to calculate the acceptance probability, which was shown in the figures. So the difference in likelihood, here's the MH probability that we can see in this diagram. So here we calculate the metropolis probability, which either accepts or rejects. We're going to get back here. So once the MH probability is calculated, we're going to compare it with the randomly chosen value. And if it accepts, then it saves all these things. And if it rejects, then it just stays at the same position and repeats the previous iteration, and then it just repeats. So essentially, this is the code behind, and we're going to reach 100 samples. So it's done with the sampling. It's going to tell you how many it accepted. So it accepted 34 samples. which is 34% in our case because we only ran 100. It's going to tell you where the results are stored in. It's stored in the zeroed folder, and it's going to keep iterating further. Even if you delete, it's going to just go back to what the number was. And yeah, so then we can just check the posterior distributions by running this. We know what the folder number was. It was 0 in our case. And we can choose the bin size for the histogram just so that it can display in different widths. So in 10, currently our rain posterior, even though it was just 100 samples, looks like this. Oh, wait, can't see. It's going to get better and closer to the true value with more samples. And it's going to show you a trace plot of how it kept differing throughout the sampling process. And yeah, I think that's it for MCMC. And so has everyone run it on their computers? Any problems?
Sure, we'll bring the first baseline model.
Daniel, probably you could go back into your code of the likelihood and compare your likelihood with my slides of the likelihood.
Right. Yep.
And I mean, normally we've run all these things just on the sort of from a terminal or something straight from Python, but in notebooks it makes it a little bit easier. Sort of run these with a head on HPC and things like that.
Yeah, if you eventually do a project like application of this to some domain, then I think the chances of you using a notebook is quite less. So you will be usually using a high performance computing and the main Python script with it. So it's good to get rid of the notebook book at some point. Then bring it back to show others.
I think Raman has demonstrated that you can actually do some stuff with notebooks too.
Okay.
Yeah, you can. But he's right.
No.
Easiest is to just about Sure. Yeah.
But I guess it depends also on the expectation. Like,
Yeah, depends on how much time you want.
Yeah, so the other major thing is that the Badlands is just an example of a geoscientific model. There would be many other examples, like you guys working underwater. There could be a smaller version of that example somehow. If there could be, then we could do something.
Yeah.
Any questions or?
I have a few, well, I have one question. So we talked about that some of these variables or parameters are both time varying, but also regionally varying. Right? But what about the initial surface, like in real underworld models that you might want to run?
Mm-hmm.
You know, you can essentially create a random, not a random, you could guess an initial surface. And you then you're essentially forcing the end result. Sorry.
So wait, so you're saying like if we don't know the initial surface, we're giving it a random one and trying to get to the end one forcefully.
That's what we often have to do with a bad line.
Yeah, I think we're just doing that and saving the process of you trying out all these values without knowing a heuristic way of whether you're reaching the right one or not. So this algorithm will do that for you, and you won't have to think about whether I'm going towards or closer to the real value by manually trying all of them. So
I guess the assumption is that your initial surface that you've made is your best guess.
Yes,
and then
there is some probabilistic
parameters you give to Badlands
will be according to that
by this process.
Yes.
So what we're really testing is do the parameters that were chosen evolve that surface we've chosen to the true value?
For correction.
Yeah.
Does do they tell you stands for height?
But yeah, I mean, it's a broader philosophical question. Like,
Like, are we actually learning more about the truth
Yeah.
of these parameters? Or we just want certainty? Yeah.
because like I can see it works beautifully in these synthetic models because you
Yep.
have the known value.
True.
But in reality,
It's gonna be much tougher.
you don't
Yes.
know that initial surface.
No, so we are going to work on another future project where we will also look at the initial surface. So we are going to so for the initial surface, let's say that because it's millions of years old, then only you have some sparse information. You may have data. Let's say you look at Australia, you may have data about initial surface of Australia 10 million years ago, only in places where there have been some geochemical exploration. But in the places where there's no exploration, you wouldn't have data. So we would need to use the data that where you have the exploration and reconstruct the initial surface. And constructing the initial surface is again an inference process. So we will have more parameters. And Nathan.
I'll take care of it.
Yeah, like Nathan is taking care of it.
But yeah, right. It's like all about the parameters, like learning.
Yes.
It's more about learning how those parameters fit. Rather than, well, we know that we will never get a complete one.
Yeah, you could just have region-based
Caveat to
distributions of heights. You could just have region-based, like you could divide Australia into a number of grids, and just in that grid you could have a distribution of heights. So instead of starting from the initial, like we are starting from a deterministic approach, So, but we'll draw from the distribution
where I was.
and then start variance from there. So each
How
time
to
we're
do that.
running
So when you
the
minimize it, like
variance, we are
coordinates.
drawing the initial surface as well. So that would be the it's going to be a bit complicated because it's the real world problem.
So you can verify the things that's produced by your MCMC by just going into the creator. So images in each example will tell you what the initial and final were for the simulated topography. So I've opened them up here. So like in this case, our initial was started at this thing, and it goes on to this, even though it's not much change because we've chosen certain parameters and only ran it for a small simulation. You can also go into your, so it's going to, the MCMC is going to form another folder called MCMC results, and it's going to have plots. So you can have a look at what this plot says it's going to look like. Whoa. And if you want to visually inspect it and see whether it looks the same or not, we can verify that. Actually, just show the slides because they have it. So like your MCMC run will have pictures of this and this. And this is the simulated one, and the predicted one is the one that I've just opened up here somewhere. Help me out.
And 1 by 3.
Yeah. How do I minimize this? Like as in zoom out. Essentially, like this is what our simulated truth was, and this is what we get from MCMC using 100 samples. So clearly there isn't a ridge-like surface that was produced when we ran it for more years and more samples. So it's eventually going to reach exactly what the simulated topography looks like.
Note this is the surface that is produced by Baselands. That's a mean prediction of like 100 samples. So all those samples that were accepted in that 100 samples that we ran, there were 34 24 of them were accepted, right? So it's a mean of that 24. So each sample produces a surface, and just you make the mean of them, and that's what we are.
Yeah, and that should be ideally the closest to the ground truth that we got initially. Yeah, I think then Nathan can just start on the demonstration on parallel tempering, which is an extension of this. Thank you.
So, which coefficient would you take then for your and
The mean of all the accepted ones.
the mean?
The mean of all the accepted ones.
So
And-
that's basically what we call the posterior. The mean.
So the histogram sort of
Yeah,
shows
the
that.
histogram.
Where's the presentation? Maybe I just show it here. So essentially, you will take the mean of all these accepted ones. There'll be a lot of repeated ones, so obviously the mean will be closer to this because this has more weightage. So you'll just take the mean of all these accepted values in the histogram. That should be the closest one to your simulated truth. Yeah, go on.
So in the example you showed us, you set a limit for when a range for M and N.
Yeah, we initially tried varying them as well. But
Yeah, because it's not varying here.
yeah, we kept them constant in this example just to show the difference between
Maybe
gain
we'll
and
start by giving the NP example.
But in the parallel tempering one,
of a
we will
uniform
change them.
distribution in a normal distribution. Just tell them what that is. And I will explain. The NumPy uniform distribution. How do you draw from a uniform
I
distribution?
don't know what that is. I mean, I do, but
You could show how you draw from the uniform distribution.
Yeah.
You already showed the
Yeah.
code. Okay, fine. Actually, so just another thing. So if you could show that posterior. So yes, if you could see this posterior, actually, you have seen that normal curve, right? So that's a normal distribution, the Gaussian or the normal distribution. So what we do, we interpolate a normal distribution on top of it. So and then with this you get the mean, and with the mean and the standard deviation, you basically get the normal distribution, right? And then basically, instead of saying that the rainfall is 1.5, we will say the rainfall value lies in this posterior normal distribution with a mean of 1.5 and a standard deviation of 0.5, let's say. And then the Bayesian approach is that you don't give an exact value to anybody. You would be like, draw from the distribution, and the chances of you getting 1.5 is the highest. So you are going to get 1.6, so you are not going to give an exact value anymore. You are giving distributions. So this is the main philosophy of using Bayesian approach. So yeah. Sure. so if you want to say what is the actual value, we are not giving you any actual value. We're just giving distributions, and then you can use those distributions and generate values, and then from there you generate predictions, and from those generated values, the predictions, you can get more of the uncertainties, of all those predictions if you combine them together. So that's the main goal of the inference. Okay.
cool.
Sorry, Nathan.
No worries. So I think the final notebook that we'll kind of look at is this PT Baselands crater example. So it's the same example we just did with the MCMC Bayesian approach, but this time we're using the parallel tempering method. And so it has similar sort of introduction. And I'll just point out the algorithm sort of extends upon from the initial Baselands sort of algorithm, the Metropolis Hastings one. Now we have the Metropolis Hastings with the parallel tempering, which adds that extra sort of temperature variable where it heats up the chains, and so they explore different parameter spaces. Okay, and that's what that's explaining. Okay, and the first figure in there shows, I guess, what Rohit has shown, the difference between the straight Bayesian one and the parallel tempered one. And so this is exploring the rainfall parameter again, and you can see there are, I think there's 24 different chains all exploring all over the place, whereas in the MCMC one was just the one chain exploring, and sort of explores a much sort of greater range. It didn't actually pick up I think the true value was 1.5 here, and it got a little bit there, but it's still clustered around one of these suboptimal values too.
So, but both of them are, neither of those approaches of the 1.5.
No, well, that's the nature of the problem. Like, because of these suboptimal values, it could be good enough. Like,
Sure.
Yeah. Okay. This is set up kind of exactly the same way. We import some things that we need. I'll run that. We set up our folder. So yeah, the problem folder again. This just has the input nodes, so our initial surface. We also have our initial XML file that describes the problem for us, but then we can manipulate the values a bit. So we set our simulation time. So we'll run this. What Daniel do? 50,000. Oops. These new Macs. Macs don't need to lock my computer. Okay. All right. So resolution factor, we'll keep it at 1. We'll run 100 samples. Keep the sediments on. This notebook's just written a bit differently because I did this one, Daniel did the other one, but it's basically the same thing. So and we've got N and M varying this time between 0 and 2. Got our rain varying from 0 to 3 here. Our erosion varying from 3 times 10 to the minus 6 to 7 times 10 to the minus 6. And then we put them in some vectors there where we can draw our sample from. And then I guess the difference here is that we have this step size ratio, and this kind of determines how much our chain is sort of exploring around how big the steps are that we take in each of our parameters. And so then this 0.02, like very somewhat arbitrary to your problem and also to your parameter.
So for the erodibility,
Well, so it's this, and then it gets multiplied by the value. So that's like a ratio. And again, we have our sort of arbitrary erosion coordinates there. And then we load in some other things. We have to set our true values here because we know what the solution to the problem is. As Daniel showed with that, where we ran Badlands once to generate our true solution file. And this is what you're talking about.
Yeah,
uniform
so drawing from a uniform distribution. So that's the code. So basically, it's you could draw from if it's a random dot normal. There's another function that you draw from a normal distribution, and this is drawing from a uniform distribution.
So it's taking these numbers, each set of these numbers, and drawing from a uniform distribution between them. And that's it. We then load in our solution file, I guess, our real solution that we developed by running Badlands once. And then we set up just our output directories as well. Did I run these? Let's make sure I run them. So we'll do that. Nothing too exciting. And then a couple more parallel tempering things. We have to specify the number of chains. So that essentially is how many cores you have on your computer, and your method will sort of go as fast as your slowest chain. So if you have 4 cores and 3 of them finish really quickly, then they have to wait around for the 4th one to finish exploring before it comes back and communicates with the other 4. So that's why Rohit showed that figure of the diminishing returns as you increase the number of threads, because you're always waiting for that slowest chain.
so is it to always have to this barrier? Can you do something where actually you don't have to wait for the slowest to start the others?
No, because you need to swap. So
but you can't swap between 2 of them, not knowing.
Like they'll swap, but they can't continue further than the last one.
But you have to wait for all the chain, right? consider all swaps.
Otherwise,
Before swapping.
we concurrency issues.
So one other thing is, if this is number of chains is 4, what it means you are going to run 5 processes because there is a master and manager chain as well. So there's a management process. So what happens eventually, like if you run this in a computer that just has 1 core, this will still run. It's just that it will not be that fast. So this code is very, I mean, it can be deployed in any architecture.
So your master is sitting there for
Your master is just waiting
Just-
for the swaps and it's just coordinating all the swaps.
Yeah, calculate the step probability and the step, that's the job of the master.
And-
The manager for
I have found that the master doesn't use that much CPU, so it's not like that big a deal. So this is all with the Python multiprocessing library, so it uses, I guess, that as best it can. Yeah, okay, and then there's a few other things like the ratio, how frequently the chains swap. These are really problem dependent on how many samples you have, things like that. Kind of need to explore around how many things just to explore before you start to actually get results. The maximum temperature, so we have this little equation that determines what our maximum temperature will be, and yeah, and there's all these variations in parallel tempering algorithms and everything that probably Rohit could speak for days on, but this is the one that we're using. Okay, so we're on that one. That just tells us everything it's picked and determined. And then this should take probably a quarter of the time of what Daniel's one, because I think I have maybe. Sorry?
My
Oh.
time to 250 seconds.
250 seconds? Okay, let's go. Did I do 100 samples as well? So you can see each temperature. So there are 4 temperatures and they've got 25 samples each, basically. And so that should go down. There we go. 2, 2, 3. Start. So while it's running, shouldn't take too long. We can have a quick look at the script and catch it. Let's open up. So yeah, all the notebooks are in the examples folder. You probably figured out, and they all generally call these scripts that do all the work in the background. This one's called PT Baselands.
to get all those, like it was a bit of work to, because all of those chains will be giving their own output files, like the predictions and the posterior files. So it's basically you have to combine all of them together, and then they can show that later where we combine.
Okay, so there's a lot going on, I guess, in this script, like a 1,000 lines or something. But the most familiar part will be here, where model equals Badlands model. So this is actually where Badlands is eventually run each time. So just like we saw before in the examples, that's where the Badlands model is instantiated. The XML file is loaded, but then this is where we change all the parameters. So we change them to whatever our current parameter selection is. So we give it the rainfall and erodibility values and so on. And then we can also put the sea aerial and sea marine and uplift parameters in there too at the moment. Okay, and then it actually runs the Badlands model, and yeah, then a lot happens. We figure out the likelihoods, so on and so forth, just like very similar to what Daniel did before. And eventually the chains are brought back together. Let's see how we go. Is that the one we're running? That's the one we're running. Okay. We're up to 21 and 25. So any questions at the moment? All good? Cool. So yeah, remember, it's all just getting it from that Badlands XML file. So it works exactly the same. And yeah, we were running this on Artemis with 48 cores. I tested it, I think, really quickly across multiple nodes, but found that it didn't communicate well. But I think I just tested it once and went like, oh, it doesn't work. Might be something to revisit. But so 48 cores is the most number of cores we have on a single node. And so that was running well. Okay, and cool, it's finished. Let's see, then we get some more results here. So here's our likelihood, I believe, is the first figure. For each chain has its own likelihood. These are the accepted proposals, so each chain accepts more and more as time goes by. And took three minutes. What's that? 180 seconds. So not perfect.
It doesn't make that much of a difference.
Yeah.
Right?
Yeah.
Smaller programs.
That top chart,
Yep.
you have the likelihood. One's flat, one's really thick. Do you have an interpretation for that? If one got stuck on a local minimum, is that why it's flat or something?
Yeah, it's probably. This is the one that is the likelihood is multiplied by 1 over t. So the likelihood actually is the same, but
With different temperatures, the likelihood is different.
so this is what. Yeah.
So this is the likelihood of each chain multiplied by its own temperature.
Oh, okay.
So the likelihood is the same, but it's just kind of, you could see it's kind of scaled by the temperature.
Each chain looks at the likelihood. So the red one, like that is what the likelihood looks like when it's exploding at a higher temperature.
Okay.
And the blue one is the one, I think, is the one temperature which doesn't multiply.
Yeah, so the blue one is the actual likelihood, whereas the other ones is the temperature. They are kind of multiplied by the 1 over temperature. So they are kind of smoother likelihood, so that it's easier for you to move around.
So let's,
Does that explain the jumps?
We don't have jumps in there, do we?
Sorry, the acceptance. So the smoother one would have this inversely proportional or something?
So the smoother the one, the more it accepts.
okay.
We have to see.
So the distribution plotted, it was the true value was 1.5. It was searching around 2. So it didn't do, I guess, too well at exploring. It was only 100 samples, so it's okay. But you can see they all start sort of around 1.9 and then explore out. So that was for the rainfall, I think, showing that. And there we go. There's our estimated topography. What happened to the actual ground truth?
Oh, it's very close to this.
It's on top of it.
Is it? Okay. There we go. Oh, that's right, because we recreated the ground truth probably earlier. Yeah. So, yeah, I guess the outcomes are kind of similar to the straight MCMC, but this one just lets you be a bit faster, explore the parameter space a little bit differently, and they're the main two benefits, I think, of this method. So, yes, I was going to say, are there questions, or do you want me to delve into any particular part of it that while we're here, or?
Generally, would you run it until that top curve before lines all converge?
Also,
that way, maybe jumping around the 1.5, so as convergence, we don't expect to get
Yeah, exactly. So on 100 samples, the line would look different compared to 100,000. That's when you generally see that.
Yeah. Right. You guys do a burning too?
Yep.
Yeah, it was 10% of the samples.
Yeah.
Yeah. So that we just set that earlier. That was one of the many parameters that you can one of the knobs that you can tweak, you know.
Can you explain that a little bit more, the burning?
You could see burning as the optimization stage, and in the optimization stage, when you are progressing, basically, you are in poor solution areas, and you don't want to put that part of the posterior of the actual parameter.
Go to the chart, top chart, maximum.
So we ignore that 10%
sorry.
or 15%.
Yeah. So where's jumping around and stuff? Correct me if I'm wrong, mate. Where's jumping around and stuff, the parameters are jumping around. So you don't want to include them because basically you take the end and you kind of find the average to find what's in. But you don't want to take the first 10 or 20% as a conversion, it's jumping around.
So there's a wide opinion on what the burden should be. Some people think it should be like half the sampling scheme. Some people think 2 to 3% is enough. But again, whenever you're confident that it reaches closer to an optimal solution, you can burn in the field first. So that doesn't include the posterior distribution. Look much neater.
I tend to look at it. I'll look at it and go, it's converged now.
Yeah.
You know, so just as long as my estimation section is in the converged bit.
Cool. Yeah. Any other questions or any part that you want to learn more about or get into or anything?
Maybe that probably would just show the code that kind of shows, you know, the MCMC class and the multi-parallel tempering class. Because we are basically, this code is reusing the code that Daniel was showing. So in there was one MCMC class, and now we have another class, parallel tempering class. And that class is basically calling the MCMC class and making, replicas of it, and then putting it into cores, basically.
Yep, exactly. So yeah, we have this Python class. So we create like this object, which then it's a bit different to the MC. So yeah, the initializing chains ones is, I guess, a significant different where we assign the temperatures and things like that, and we give it these swap procedures as well. So this is where it decides whether, based on our proposed likelihood, whether we're going to swap the chains or not. So exciting stuff, and then we run them. Yeah.
So sorry to keep asking questions.
No, that's good.
So again, you run it to a convergence, but you've got 4 chains. I don't quite get the temperature, but I get the concept of weighting somehow a bit different.
Yeah, that's a good way to think of it. Yeah.
So you've got 2 of them converged and 2 of them haven't, and it somehow merges their estimates. And would you usually run it? Yes, look at that. You've got two of the chains of converged and 2 haven't, approximately. Do you keep running it till all 4 converge? Or what happens if one of them never converges? Would you not put that chain? That's a good thing. Given that.
Yeah, if it has, there still has multimodal likelihood. We're not really sure whether there's only one big mode or several equally likely peaks in the likelihood. So there is a chance that even that one thing that doesn't look like it's diverged sort of is on, let's say, another likely solution. Because during the sampling process, you can't tell if it's like on a good peak or not. We generally include all chains in this system to plate that iterates into the posterior. So
even when we make the answer that we know, we still don't know whether it's the right answer. So
yeah, essentially.
Okay. So I guess you can explore why one change isn't converging.
yeah.
Mostly, they don't tell you whether it would be
Yeah, so ideally, like the algorithm should correct itself, like one of the things is not converting. We like ideally it will swap and go to a higher temperature and get closer to the solution, and then swap back to a lower temperature to find its way closer, even closer. But yeah, in most cases, not all of the chains will converge at a certain point. So you just tend to.
Oh, sorry, I didn't mean they all have to converge at the same point. I mean they all flatten out.
Converge into their own solution as well.
Yeah, so you look for that. You look for them just to flatten.
To flatten them out. So again, we can't control when they flatten, but we can try different sample sizes until we see that all of them do.
So that's what I meant. If one of those chains doesn't even wind up flattening out,
I think we still get a quite comprehensive solution, even if one of them doesn't.
would you use that one or would you go with that chain?
Yeah, good.
Cool. So just kind of recapping a bit, I guess. I think we've just had a crash course in Baselands and what it's capable of, and a little bit about how to run it. So we just went through the the various notebooks. Firstly, we all learned how to use Docker, well, I did, which was good for me. So we learned how to create the input that's required for Badlands. We then saw how to sort of manipulate that input with the XML files, again with Badlands and PyBadlands specifically. Then we saw how we need to run Badlands once to create a final surface and an initial surface to sort of compare our solutions to, which obviously in the real world, we don't have that. So that's one of the challenges that I guess we've discussed a little bit here. And then we just saw the straight MCMC implementation of it, and then also the parallel tempering version as well. Oh, this little summary here, yeah. And yeah, so hopefully, like from today, I guess you can take away that this thing Baselands exists, and if you find your own Badlands modeling could do with just a little bit more exploration or something, then hopefully get started in that respect. So feel free to reach out to us if you have more questions specifically or anything like that. And Rohit, do you want to add anything? Is this live streamed to Facebook?
Yeah, I think the point is that all we are presenting with this paper is introducing parallel tempering in a multi-core framework and using Badlands as an example to show that it could be done for other models in the geoscientific community. And what we want is to kind of collaborate and work together and explore what those other models are. And we, on the side, we have also been working on one of those other models. That's the PyReef model. And we will be also using this multi-core parallel tempering approach for modeling the Great Barrier Reef for the last 10,000 years. And that's a PhD project that we have defined. And me and Jody Webster and Deep Property Muller. So and in there we are going to use parallel tempering, and we are going to do all those things that we discussed about, like improving